Alright, so this week is section 8.4, adding and subtracting rational expressions. So we're going to start with this equation here. Now the key to doing this is to try to break this up into pieces, for one, so that the numbers that remain under the radical are all the same from one expression to the next, and by that I mean from this expression to this expression to this expression. And also you want to try to factor out what I call perfect squares. If you don't know what I mean by that, I would do a search in Google engine. I'll find out, but a quick summary: 2 squared equals 4, so 4 is a perfect square. 3 squared equals 9, so 9 is a perfect square, and so on and so forth down the line. Okay? So I would keep a table of those handy if you don't know them off the top of your head, because it can make these problems go a little quicker. So again, we're going to break up each one of these radicals into multiple pieces. And this is one of the cool properties of radicals, is if you have terms that are multiplied together underneath the radical, you can split them apart like this. Okay, so since we had 72 times m squared, we can break that into the square root of 72 times the square root of m squared. So I'm going to keep doing the same thing across here. Alright, and now in each one of these, we have this square root of m squared. Well, that simplifies down to just m in each one of these terms. So that's nice and handy, and we can just bring that out in front here. So now we've got 3m times the square root of 72, and now we're going to start breaking this apart into smaller pieces. So I'm going to ask myself, what is the largest perfect square that goes into 72? Now, I believe 4 works, but 4 is not actually the biggest perfect square that we can use. If you keep trying, you'll find that 36 will work.
Oh, this is the class.
Sorry, minor interruption there. All right, let's keep going. All right, so we're going to break this 72 into 36 times 2. Now 36 is 6 squared, so that's a perfect square. All right, so I'm going to keep working my way across here. So I'm going to bring my m again out in front. I'm going to break that 32 into pieces. Well, again, if I think about it, 4 would work, but 16 works better. Now, is it the end of the world if you don't find the best perfect square to use it right off the bat? No, not at all. So actually, let's illustrate it with this one. Let's say I used the 4. And I broke this instead into 4 times 8. Well, if you look at this 8, you'd ask yourself, okay, are there any other perfect squares that divide into this number? As it turns out, there is. 4 does, right? 8 can be broken into 4 times 2. So you just pull this 4 out and do 4 times 4, which would give you our 16 times 2. Okay, so to assure yourself you've got the largest perfect square, just keep breaking down your numbers until you're left with a perfect square and something that cannot be divided by another perfect square. Okay? Alright, so now lastly we're going to tackle this 18. Again, I brought that m out in front. 18 I'm going to break down to 9 times 2. Okay. Now that I have these broken down, I can do the same break apart thing that I did up initially here. So I have 3m times the square root of 36 times the square root of 2 minus 5m times the square root of 16 times the square root of 2 minus 3m times the square root of 9 times the square root of 2. Okay? And now, since all of these are perfect squares, these all work out into nice, neat, pretty integers. Okay? So I now have, instead of 3 times m times 36, or the square root of 36, I have 3m times 6 times the square root of 2 minus 5 times m times 4 times the square root of 2 minus 3 times m times, I'm sorry, oops, there shouldn't be a square root there. Whew. Working on autopilot. Alright. So we've got 3 times m times 3 times the square root of 2. Okay, now I can combine all of these constants together out in the front. So I've got 3 times 6. So I've got 18m times the square root of 2 minus, so I've got 5 times 4 here, which 20m times the square root of 2. And I've got 3 times 3 here, which is 9m times the square root of 2. Now, again, once we've gotten to this point, we can see the goal for trying to leave the same number underneath all the radicals. If you can do that, then you can combine these because they are like terms. You can think of these numbers, or the radicals with the numbers underneath, as like an x. These all have to match, all these numbers, in order for us to combine these terms together. And since they do, we can look at the constants separately, work this out. Again, that's 18 minus 20 minus 9, and that gives us a negative 11 times m times the square root of 2. Okay? All right, so I'm going to move on to another example now. Okay, so we're going to take this example, and we're going to use the same sort of properties that we did on the multiplication. When you've got two terms under a radical that are being divided, you can split that radical up into the numerator and into the denominator. So this is the same thing as the square root of 25 over the square root of x to the 8 plus the square root of 9 over the square root of x to the 6th. Okay, now hopefully these numerators should be relatively easy to simplify. The square root of 25 is just 5. The square root of 9 is just 3. The denominators may not be so clear. So the way I like to think of these is, again, oops, there should be an 8 there. So instead of thinking of it as a root, I like to think of it as an exponent. And the square root, the exponent that matches it is 1/2. And then again, from here, we can use our product rule for exponents. So we've got 8 times 1/2, which is x to the 4th. Okay? So the square root of x to the 8th is x to the 4th. Okay? If we do the same thing for x to the 6th, you're essentially just dividing that exponent in half when you take the square root. So it's x to the 3rd. Okay, now in order to add these two fractions together, we need the common denominator like we did with the last section. So I'm looking at the highest exponent, which in this case is the 4. So I'm going to change this fraction over here so that it has the same denominator as this one. I'm going to do that by multiplying both the numerator and the denominator by x. Okay, so that gives us 5 over x to the 4th plus 3x over x to the 4th. Okay, and now since these are the same denominator, I can combine the terms in the numerator, put them over the common denominator. And that's it for this problem. Please let me know if you have any questions on this section.